All right, it's just after 10 o'clock, so we'll go ahead and get going this morning. This is the low dropout regulator educational session. I wanted to remind everybody that the educational sessions are no charge. They are sponsored by Cadence this year. I also want to remind you that if you aren't familiar, if you go to the website, you can find a link to rate the educational sessions. So if you go to the CICC website and go to program, you'll be able to scroll down, you'll see each of them, and then at the end of the session you'll be able to provide comments as well as a numerical rating. And this will give us great feedback for future sessions. So today I'm pleased to introduce our speaker. Pavan Hanumolu is currently an associate professor in the Department of Electrical and Computer Engineering at the University of Illinois, Champaign, Urbana, and he's received the Ph.D. from the School of Electrical Engineering and Computer Science at Oregon State University in 2006, where he has subsequently served as a faculty member till 2013. His research interests are in energy-efficient integrated circuit implementation of analog and digital signal processing, sensor interfaces, wireline communication, and power conversion.
Thank you, Tim. And after that introduction, it's only downhill from here on. I'm excited to be here. I've known Eric for a long time, and I'm a big fan of CICC. And I couldn't say no for this opportunity. What I would like to do today is talk to you about low dropout regulators. Because this is an EdSession, hopefully at a level that everybody can follow, and also hopefully when you read other advanced stuff, it would make a little bit more sense than it does now. For instance, I think this is recorded, so I don't know the rules for asking questions. Maybe you can ask me at the very end if that is not a problem. So let me briefly spend some time so that everybody is on the same page. First of all, this is what I think of as the role of an low dropout regulator is. In a typical power management system, what you have is a DC to DC converter shown here, which provides most of the power, and then you have many circuit blocks that needs to have supply voltages that meet certain requirements. For example, if you take analog and mixed signal and RF, the power supply noise is an extremely critical parameter, and we'll talk a lot about how to suppress power supply noise in the output of the LDO. And in circuits where you have a lot of switching, for example, digital circuits, isolation also becomes important. You don't want, for example, if this is a large digital system, you don't want to have any of the switching noise appearing or coupling to the output of the DC to DC converter. In that case, we are interested in reverse isolation. Right? So, so in principle, a good low dropout regulator must satisfy essentially these three requirements. It should suppress any ripple produced by the DC to DC converter, and it should provide some isolation between noise generated by the circuits to the output of the DC to DC converter. And in applications where supply noise is of critical importance, it should take a noisy input, in this instance supply voltage, and provide a clean supply to the sensitive circuits. What I'm not showing here is one other case when this is battery voltage. If this is a battery voltage, the regulation is primarily done by the DC to DC converter. In some applications, the battery voltage might itself be an input to the LDO, in which case there are a few other considerations that we need to pay close attention to. But this is the context in which I'm going to talk about design and the intuition behind the design of low dropout regulators. Okay, so one easy way to actually implement a low dropout regulator is, for example, if this VN is not the VN that you are looking for, then one could possibly use a simple resistive divider and generate an output that meets the required ratio between Vout and Vin. And clearly, this is not good, but I just wanted to show that a good place to start is the simplest thing, and I couldn't find anything simpler than a resistive divider. The problem with this is if the load current changes, the output voltage changes, and as a result, this is not really providing the desired output voltage. So in that case, one possible way to regulate the output is to simply change the resistor divider. Right? You change the resistor divider using well, I'll show in the next slide, using some kind of feedback such that the output remains some fraction of the input at all input voltages, right? So feedback regulates are in such that V out is some fixed value, fixed being some desired reference voltage. So this is how almost all the LDOs are implemented. You choose your variable resistor, maybe an NPN or NMOS or PMOS. We'll talk about these. I'll refer to as pass devices. There are many choices for the pass devices, which we will discuss shortly. And this is the simple feedback loop. So the feedback loop now is forcing the output voltage here, or the fraction of the output voltage to the reference voltage. And if this feedback is good enough, then for any values of these RLs, your output is going to be some beta times VREP, regardless of the output current. Right? So at a very high level, that's at least minimum requirement that an LDO should satisfy. Right? So if you take a much closer look at these LDOs, what you find is the following. You have the feedback network shown here, which consists of an error amplifier, because it's going to measure the error between the desired or the reference voltage and whatever is the fraction of the output voltage, and it's going to regulate a pass device. Previously, I have shown this pass device as a simple variable resistor, but this pass device, as we will see shortly, could be either an NMOS, PMOS, or NPN, PNP. And the feedback resistors typically are chosen because this reference voltage is fixed. Perhaps you have a band gap which provides you 1.2 volts, but this output voltage needs to be regulated to maybe 1.8 or 2 volts, in which case you just use the divider and vary the one of the resistances, typically RF2, in order to generate the desired output voltage from a fixed reference voltage. Right? So, and sometimes it also requires some startup circuitry to turn on to make sure that the reference voltage is actually giving the reference voltage, and so on and so forth. What I would like to do today is only focus on this portion of the LDO. I'm going to assume that we are given a good reference voltage, and we want to force the output voltage to the desired value. Right? So that will be the regulation. That I'll refer to as the regulation loop. Okay. So with that in mind, what I would like to do is start off with describing the performance metrics. These are the goodness metrics of an LDO, and then address two important aspects of an LDO design. First of all, this is a feedback loop, so one has to ensure that it is stable, and it has to be stable under varying output load capacitances and also varying load currents. That's what makes the stability of LDOs slightly more complicated than, let us say, a standalone amplifier which is driving a fixed load. Right? So we'll spend some time on stability. And towards the end, I'll also talk a little bit more on power supply rejection. This probably is the most important characteristic of LDOs used in SOCs. So this will be the plan for the next 1.5 hours or so. So the performance metrics are many. I mean, for any analog building block, you can always come up with power. We want the lowest power, lowest noise, so on and so forth. But what I would like to do today is focus on LDO specific performance metrics, such as power supply rejection ratio and efficiency, and in particular the regulation metrics. We'll talk more about these three: load regulation, light regulation, whether it is static or dynamic. Static meaning you have all the time in the world to wait and see what the output voltage is, and dynamic is when you are changing either the input voltage or the load current. How does the output voltage behave? That will be the dynamic aspect of this regulation. Okay, so let's take a closer look at each of these parameters, starting with dropout voltage. So dropout voltage is essentially, again, I'll use this picture to illustrate the performance metrics. Here, where I'm plotting V out versus V in. It would be nice to have V out to be at a fixed value regardless of whatever the input voltage is, but most practical LDOs require some minimum amount of V in order to regulate the output voltage at the desired value, this being the desired value. So dropout voltage is defined as the difference between V in and V out, at which V out is no longer regulated. This could be typically in the range of 0.1 volts to maybe 400, 500 millivolts, or in that range. Clearly, the exact value of the dropout voltage will depend on the kind of pass device you use and how much load currents you have, either PMOS or NMOS, and we'll describe those things later. But typically, as I've indicated, these are somewhere in the range of 0.1 to 0.5 volts. Ideally, we would like to have as low a dropout voltage as possible, but in practice, dropout voltage is often traded off with power supply rejection and even low transient and things of that nature. So we would like to understand how those trade-offs work based on this definition. Okay, so the second, probably not so important parameter is the so-called quiescent current. Again, this LDO is the big picture LDO where I'm including the reference generator, startup circuitry, error amplifier, everything. And you need some amount of bias current in order to make the feedback elements work properly. So this quiescent current is essentially the bias current consumed in all these building blocks. So if you are using a MOS type pass device whose gate current is zero regardless of drain source current, then quiescent current remains almost constant independent of the load current. But if you are using an NPN kind of a pass device, then the base current is a weak function. Depending on the current gain factor, is a function of the load current. In those cases, the quiescent current somewhat varies with the load current, but in this, for today, we are going to mostly focus on MOS pass devices. Therefore, this quiescent current is almost independent of the load current. Okay, so the second important aspect that comes in because of the quiescent current is so-called current efficiency. For power converters, typically you define efficiency as power efficiency, but for LDOs, we'll come to the power efficiency shortly, but for LDOs, people also refer to efficiency as current efficiency, which is not surprisingly I out over I in. And I in is the current drawn from the input, so it's I out plus the quiescent current that I defined in the previous slide. So the second efficiency is power efficiency, which is output power, I out over, times V out over input power. And if quiescent current is small compared to the output current, then this boils down to V out over V in percentage. Okay, so as an example, this is for your reference. By the way, I forgot to mention this. Some of the slides you have, I cleaned them up, so I apologize for late changes. But on the first slide, I have indicated the URL to download these slides. So maybe I can just quickly flash. Okay, I'll show you at the very end. If I forget, Eric will remind me to advertise the link from which you can download these slides. So, a simple example shows that the current efficiency is 99.8% for the choices of output current and quiescent current, and the power efficiency is 72%. And this is one of the reasons why people would like to show current efficiency, even though for all practical purposes it's sort of meaningless parameter, because 99.8% sounds so much better than 72%, right? So we'll have to be somewhat careful. If you can get power efficiencies in this range, then it's equivalent to solving world hunger, for example. That's not possible, at least in our generation. The next parameter that I'm now switching to the regulation aspects of the LDO, starting with the line regulation. So this is a measure of LDO's ability to maintain the output at a fixed value in the presence of varying input. For example, if you connected battery as the input voltage, if the input voltage is getting discharged, then how does the output behave? Right? So if it stays constant independent of the input voltage, then that's good. But in practice, as I have shown in 2 cases, the green being more practical case, as you keep increasing V in, V out sort of deviates away from the desired value. And a hint for expecting this kind of behavior is we essentially have a feedback system, right, with finite loop gain, and we'll prove this a little later. But which means that in the presence of any parametric variations, unless you have infinite loop gain, you should expect changes in the output, right? This is saying essentially a way. This is defining a way to quantify that change. And again, line regulation is delta V out, changes in output voltage to changes in the input voltage. Typically, it is specified as millivolt per volt, 1 millivolt per volt at delta V in of 1 volt. That would be a very good LDO. Okay. One more thing I would like to point out is that this line regulation, at least for today's talk, I'm going to treat this as a static metric, meaning I'm going to change V in from, let us say, 1.5 volts to 1.2 volts, wait a day, and then see what the output is. Right? So that's what I mean by the static metric, because there is a line regulation, which there is another parameter which will define the dynamic behavior of the load regulation, meaning you change V in rapidly and see how the output behaves. So that is not what I will refer to as line regulation. So load regulation is similar to line regulation. Instead, we are changing the load current. So here I'm plotting a conceptual diagram of how the output voltage changes as a function of the load current. As you can see here, ideally we would want to not change the output value regardless of what the output current is, but in practice any LDO, for instance, have a finite output impedance. So when you wiggle the output voltage or when you wiggle the output current, your output voltage is going to change. By how much will depend on really what the output impedance of your LDO is, right? So and as a result, you will end up getting some variation in the desired or the output voltage as a function of the load current. Right? Ideally, we would want to have this term to be 0. So, in contrast to line regulation, we also have a dynamic metric, which I will refer to as line transient response. This is the place where you are going to change the input voltage, and you would want to measure how much output changes are you going to get. So here, so if you change input in this pulse waveform by delta V in, how much delta V out do you get is a measure of the line transient response. Again, this is somewhat similar to line regulation, except for now I'm interested in the transient behavior of the LDO. Similarly, we also have a load transient. So when I out changes by delta I load rapidly, as shown here, by how much will the output change, right? So again, by exactly how much they change will depend on, there is a typo, this should be LDR1, by how much the static load regulation is going to measure, right? So by which I mean, if I load is this value, then the static measure tells me that V out is going to be this steady state value. And if I load is this, then the static measure is going to tell me, static measure of load regulation is going to tell me that this is my output. So the line transient is going to just tell me how I'm going to transition from this voltage to that voltage. Ideally, we would like to transition very fast, and this is particularly useful in systems where we are dynamically changing behavior of the circuit. For example, if you're doing something like DVS or DVFS, so you're turning off circuits or most part of the circuits, and you're turning them back on. Right? So the load current is going to change in proportion to how much of the circuitry is active and how much is not. So that manifests itself as a load step, and as a result, we would really like to know what the load transient behavior of the LDO is. And this, I think, is perhaps the most important metric for LDOs used in SOC environments, which is the power supply rejection ratio. or power supply rejection, which I'll denote it as PSR. It's again a transfer function. How much output changes do you get when you change the input voltage? Input itself is the supply voltage in this particular case. This is similar to because Vin itself is the input, is the supply voltage and also the input voltage. It's similar to line regulation, but it is measured with respect to frequency. And it is also similar to line transient because we are actually interested in changes in input voltage translating to the output, but it is measured for small signal variations. When people define power supply rejection ratio, they are typically measuring with small changes in input or supply voltages, 10 millivolts, 20 millivolts, or in that range. It turns out that LDOs are relatively linear systems in the sense that even if the power supply is 50 millivolts to 100 millivolts, in most cases you can show that this power supply rejection ratio as defined here as a small signal parameter quantifies the real behavior of the circuit even in the presence of larger amplitudes in the vicinity of 50 to 100 millivolts. So if you combine all these things, we end up with this accuracy. There are many ways to combine these parameters. One way is to just add the absolute worst case for the line regulation and load regulation and add the other non-idealities in a mean square fashion, where this is the reference voltage drift. You have a band gap reference, you are generating, you are providing the reference voltage to the LDO using that, and if the reference voltage itself drifts, your output voltage cannot be any more accurate than that, and offset of the error amplifier is going to drift with temperature, and the resistance variation, the feedback resistor divider, any non-linearities associated with that are captured by here. So anyway, I mean, the more important thing to remember is not so much this equation, but these are the parameters that can go wrong when we are designing an LDO is the key takeaway. Okay, so that's sort of an overview on the performance metrics that one should be aware of while designing LDOs. So what I would like to do for the rest of the talk is talk about these different kinds of LDO architectures and discuss how what their performance metrics are based on the design choices we are going to make. So essentially, I would like to divide these into two categories based on what kind of pass device is used. Again, you can do a similar exercise for bipolar output stages, but here I'm going to focus on either PMOS or NMOS and also cap or cap-less LDOs. By cap, I mean they require an output capacitor in order to make the loop stable and make the LDO work properly. Cap-less is they would work even without connecting an external capacitor. Right? So the design trade-offs for cap and capless LDOs are slightly different, mostly in terms of stability, and we will discuss those aspects as well. So let's start with a PMOS LDO with an output capacitor. So again, a simple. This is the same picture I have shown earlier. Vout is VREP provided by a reference generator times this level shifting factor. Because this is a pass device and it requires maybe few hundred millivolts of VDS in order to act like a good current source, the dropout voltage is roughly the VDSAT of the output device, which happens to be somewhere in this range. And again, output capacitor C0 is placed off chip because this is the cap-based LDO, and it often comes with some amount of ESR. And when we discuss stability, I'm going to talk a little bit more on how to make use of ESR in order to actually stabilize this feedback loop. That we will discuss shortly. So the output voltage calculation, just for completeness sake, we can do it in multiple ways. Number one, you can just write KCLs, KVLs, blah, 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 and then you will end up with a relation from Vout to Vin as shown here, or Vout to VREF, and the overall output is basically whatever comes from Vin and whatever comes from VREF, and you sum them up together. Right? So again, there is no black magic here. The only reason why I'm showing this slide is this is not how I would like to do it. The way I would like to do it is by using a signal flow representation of the LDO, because later on when we want to do power supply rejection and a little bit more intricate LDOs, this picture will become somewhat tedious to calculate. So what I would like to instead do is represent this behavior in this form, where the feedback factor or the feedback divider is this. You take V out and apply the feedback resistor, and you got the feedback voltage, and it's subtracted from the reference voltage, and you apply the transfer function, open loop transfer function of the error amplifier, denoted here in HEA of S, and you subtract that from V in, generating the VGS, and multiplying that with the GMP, the transconductance of this pass device will give you some current here. You also have some current based on the VDS, V in minus V out. This is V in minus V out over RDS is the current generated by the output impedance. You sum them up and put it into the load, which is all of this capacitance connected in parallel. Right? So again, for simplicity, ZL is RL in parallel with this portion of the circuit. So once you have this, it turns out that we can very easily calculate the transfer functions using what is referred to as Mason's gain rule. Let me spend 2 minutes on what this is, because I'm going to use this a great deal in the following slides. So if you have a signal flow graph that looks like this, then if you're interested in figuring out the transfer function H of S from V out to V in, then what the Mason's gain rule is, I mean, this sounds complicated, but it is it's actually quite trivial. You can write the transfer function simply by eyeballing. So here, H is the transfer function that we are interested in. M, I think, is an important parameter, is the gain of feed-forward path. If there are two feed-forward paths, then M1 represents the first feed-forward path and M2 represents the second feed-forward path. Delta is the system determinant. It is 1 minus summation of all loop gains. And then you have this bunch of other terms here, which is basically all the loop gains excluding 2 at a time, 3 at a time, 4 at a time, so on and so forth. If this seems cumbersome, it is not. Let's say you have, this is a simple example, which hopefully will make it easier to understand. So if I want to figure out the transfer function from here to here, then that from previous slide, this is really the transfer function, where M is the forward path. There is only one forward path, right? So there is only M1, which is A times B times C. Delta 1 is, if you go back, this delta 1 is what are the loop gains if you remove the forward path. So if I remove this forward path, there are no more loops that are left. So delta 1 is 1. And you will have to figure out the system determinant, which is 1 minus, this delta 1 is 1 minus, you have one loop here, 2, 3, so L1 plus L2 plus L3. So if you remove the first one, then you have L2, L3. If you remove the second one, you have L3, L1, so on and so forth. And the third term is the product of all the loops, L1, L2, L3. So the transfer function now essentially becomes this. So if you have to apply KCLs, KVLs at these nodes, as you can imagine, it's a little bit more tedious. So I'm going to use that in calculating the output voltage, for example, in this case, due to VREP. So if I'm interested in calculating from VREP to V out, I would figure out the forward path, which is HEA of S, GMP times load. That's the forward path. It's shown here. I'm doing this at DC. Therefore, HE, the transfer function of the error amplifier is just the DC gain. GMP and ZL is just RFL as shown here at DC. So that's the feed-forward path. And in the denominator, you have, if you remove this feed-forward path, there are no more loops. So this is 1. Typically, for all like 90% of the things that we are interested in, it's always going to look like 1. Plus, there are 2 loops. One loop is this EA0, GMP, or RFL, this loop. That term is shown here. There is another loop that is this, and that term is shown here. So if you simplify, what you will end up getting is V out over VREF is this, but after even more simplification, it is approximately equal to 1 over beta, as long as you have large DC gain in your error amplifier. Right? So this again is not too surprising. And if you want to calculate the output voltage due to V in, you can exactly do the same, which is now you have 2 feed-forward paths. You can go to the output either through this or through that. So those two feedforward paths are added together. And the denominator, if you do it once, it's free. The denominator remains the same for any trans function that you are interested in. So, so this is same as what you have seen in the previous slide. Okay. So after some simplification, what you find is V out over V in is 1 over the DC gain times feedback factor. So what this means is line regulation, as you may recall, is how much changes do you get in the output when you change input is really equal to this based on previous transfer function calculation. So really, if you want excellent line regulation, all this is saying is build an amplifier with a very large DC gain, right? Again, for those of you who have used, all of you who have used feedback, this is not at all surprising. But one thing I would also like to point out is there are other sources of error in the output voltage, which are the sources that come from the reference voltage, which we just calculated, and the reference voltage and offset are one and the same because they are at the input of the error amplifier. Those are divided by beta, and this I know from the transfer function we calculated 2 slides ago. So what this is saying is, if you have very large loop gain, your output accuracy can be maintained very well because this term is going to be 0. But feedback factor, right? I mean, this will be 1/3, 1/4. So any changes in the reference voltage and the offset voltage sort of get amplified by the feedback factor. So for that reason, it's not only required to have very good error amplifier, we should also need to make sure that the offset of the error amplifier sort of doesn't drift away. Okay. The second aspect is load regulation for the PMOS LDO. Again, the load regulation is, if you may recall, how much output voltage changes because of I out, and you can. The way to do this is you apply a small delta I out current here and see how much delta V out changes you get, by doing that, so this should be at incremental ground. So you got some current because of changes in RDS, that's this term here, and you also have any change here because of changes in I out will get amplified by the error amplifier gain and the GM of this transistor, and that term is shown here. Okay, so I'm trying to figure out how much output current change do I get when I change delta V out, and after some simplification, you end up with RDSP, which is the output impedance of the PMOS transistor divided by 1 plus this funky character, which is the DC loop gain. So this feedback is going to attenuate the output impedance by the amount of loop gain you have. This is yet another reason why we would like to have very large gain in the error amplifier. So now I'm going to sort of switch gears and talk about many things that can go wrong with LDOs. The first being stability. So stability is, if anybody says feedback is good, the same people should also tell you that stability is an annoying thing that one has to deal with, right? So there is no escaping from stability even for LDOs. So the problem statement is the following: you have multiple poles in this loop. One at the output of the error amplifier. I have already said many times that one needs a very large gain from the amplifier, which means that you may end up with very large output impedance, which means that this pole is going to be at relatively low frequencies. And since we are placing a large capacitor at the output, there is another relatively low frequency pole at the output. There are other poles perhaps at the input of the error amplifier, but generally those tend to be beyond the loop gain, unity gain frequency, which is typically in the order of a few megahertz or so. As a result, our focus will be on making this error amplifier output pole and the LDO output pole to be widely apart in order to achieve the desired phase margin. So that separation of the loops is also referred to as frequency compensation. So there are essentially two ways to compensate. One is pole zero cancellation, and the other is pole splitting. And we'll talk these two things together. And if you are thinking, why not just do the standard Miller compensation? really Miller compensation is not all that useful if your output pole happens to be the dominant, right? I mean, Miller, the gain, you really are not doing anything to the output by doing the Miller multiplication. And if the C naught is going to be so much larger, then Miller multiplication of the compensation capacitor doesn't really solve the problem. So for output pole dominated LDOs, Miller compensation is really not an option. But we will discuss that shortly. But let me start talking about the pole zero cancellation approach. So again, for stability, I'm going to be a little bit sloppy and just use loop gain as a measure to evaluate stability. By which I mean, I'm going to evaluate the loop gain as shown here. I'm going to break the loop, and actually, if I have to be precise, then I'll also have to figure out the loading effect of the error amplifier at this node. So I can extract some input capacitance here and place it there. But modern simulators actually give you ways to actually not break the loop. For example, STB analysis in Spectre allows you to do the loop gain calculation, including the loading effects, by not physically breaking the loop. But for simplicity, even though that's how one would want to simulate here, for ease of explanation, I'm going to simply break the loop and account for all the loading effects by adding some capacitance at this node. So loop gain is simply defined as negative, the excitation is Vx here, minus Vy over Vx, and one can easily calculate this to be product of the gain of the transfunction here and the gain of the output stage as shown here. Okay, so if you want to, and I'm going to use this loop gain to actually figure out the loop stability shortly, but if you want to figure out the loop gain using all the parasitic capacitances, like for example CGDP and all that, then again, you guys know this better than I do. It can easily be calculated to be this expression. It essentially has a zero because of this feed-forward path, and then two poles as governed by this quadratic expression in the denominator, right? So, the more useful thing is to depict in this form. I'm plotting the loop gain, magnitude response versus frequency. The two poles are shown here, and this is already a red flag because you have two poles inside the loop gain, unity gain crossover frequency, and therefore the phase margin is going to be very bad. So the whole problem statement is the following: how do you achieve the phase margin in the presence of these two loops? The first approach is to actually place a zero inside the unity gain frequency so that you gain enough phase so as to achieve the desired phase margin. And in the second approach, we are going to push one of these higher frequency poles to outside the unity gain frequency. Right? So those are the two ways of compensating LDOs. And when we do this, these compensation schemes must be robust to variations in load current, because these LDOs could be used across a very wide range of load currents. And for LDOs with off-chip capacitor, you should also these things should also work with varying output capacitances. Right? So these are the additional things that one will have to keep in mind. So the first way to compensate compensate the pole is by adding a zero within the unity gain frequency, and it turns out that we can add this by simply adding RC. I mean, it could also be done by adding a series resistor here, but since this capacitor is much larger than this, you can get away with placing a low frequency pole by adding a series resistor shown here. And if you calculate the output impedance in the presence of this capacitor, you can easily see that it introduces a zero omega Z, and the new transfunction becomes as follows. Here I'm just simply ignoring the feed forward that we had because of the CGD of the past device, because that feed forward, the zero because of the feed forward is, as I have indicated, typically is at a much higher frequency. Right? So for that reason, I'm ignoring that. Okay, sorry. So how do we actually ensure that the zero frequency, which is at the newly added compensation resistor times the load capacitance, to be within the unity gain frequency. Well, we just choose whatever RC ensures that, right? So, and when if you do that, the phase margin is going to be simply determined by the ratio of how far in the zero frequency is with respect to the unity gain frequency. If they happen to be at the same place, phase margin is 45 degrees, and if zero is much lower than that, you get better than 45 degrees phase margin. So how do we actually include this compensation resistor in the feedback in the LDO? Well, majority of commercially available LDOs often specify the ESR, the series resistance of the capacitor, to be certain value in order to stabilize the LDO. Right? So this is a constraint that you will have to satisfy if you are to use that particular LDO in the first place. Obviously, this is good to stabilize, but it also comes with all this additional constraint, and this is a very annoying constraint in many instances, because most of the low ESR capacitors are these ceramic kinds, and we would like to use these because they come with very short, small footprints. But typically the ESRs are in the milliohm range and therefore cannot be used. And also, if you have a capacitor here to supply all the instantaneous current to your load, if you make the capacitor look very bad by adding a series resistor, then you are going to naturally make the transient response of the LDO much worse. So for these reasons, it would be nice to have this zero compensation without actually using a ESR in the first place. Okay, so in the next few slides, I'm going to talk about how to actually compensate LDOs without using an external ESR of the external capacitor, and therefore hopefully mitigate some of these dependencies I have indicated. Okay, so here is how one can possibly do it. You can always add a feed-forward capacitor as shown here in order to introduce a zero, because at high frequencies you really are shorting RF1, therefore you should expect a zero where the impedance of the capacitor becomes comparable to that of RF1. So if you do the the KCL KVL and figure out the transfunction from V out to node Vx, as I have shown here, and not too surprisingly, you find that at DC you got the resistor divider that we wanted, and you also get this additional stuff because of the added capacitors. And interestingly, you have a zero located at 1 over RF1 CF1, and unfortunately, you will also have to deal with the pole that comes from a parallel combination of these two resistors coming in parallel with CF1, and that is denoted here. Okay. So ideally, what we would want to have is that the zero frequency to be well within the unity gain frequency in order to stabilize the loop, and this the newly added pole frequency to be farther away from the unity gain frequency, so that we don't compromise the stability because of this newly added pole. Unfortunately, this is not what happens, because if you take the ratio of omega PF to omega ZF, you would want this ratio to be very, very large. It turns out that this is actually taking the ratio here. It turns out that this is equal to 1 plus RF1 over RF2, which is also equal to V out over VREF. And V out over VREF cannot be a factor of 100 off, right? So this typically is somewhere between 1 to 3 or 4. So as a result, this kind of adding zero, the way I'm showing it, is not directly useful for this coupling between the newly added pole and the zero frequency. So we would like to have a compensation scheme that looks like this, but doesn't add the pole that comes with this topology. So let me show you how one can eliminate that newly added pole frequency, so that we can be able to we are able to compensate it by just the zero. So for that, let me just quickly look at actually what is happening. What this capacitor is doing in terms of voltages and current. So what I'm writing here is a KCL at this node, which is V out minus Vx times this is equal to Vx over the current here. So if you rearrange these terms, bringing all Vout terms onto one side and Vx terms to the other side, and if you, I mean, I haven't really changed anything. If you take the ratio of Vx to Vout, then we have the 0 at RF1 CF1, 1 over RF1 CF1, but we also have the pole that comes from this term. So what I'm going to do now is, since I do not want the pole, I'm going to leave this term alone, and I'm going to take out any current that is coming because of this term here, so that you will end up with Vx over Vout to be 0 over some ratio. Right? So that is the goal. That is how we are going to eliminate the pole frequency. So for that, let me just go through a couple of steps here. The current flowing through the capacitor is given by the voltage across the capacitor times SCF. So I can always represent the same behavior in this form, where I'm not violating any KCLs at any point. There is ICF amount of current going into Vx, both from this side of the resistor and the top side of the resistor. So this is equivalent to essentially having the same thing represented in this manner. So if I now replace the ICF currents by these values, then what I end up getting here is the first term is V out SCF. So that is simply saying that the voltage across the capacitor is V out, and the value of the capacitor is CF. That will give you V out SCF current. So whatever is left is Vx SCF. So I'm putting that whatever leftover current here. And similarly, I can do the exact same thing on the Vx node, and I have Vx SCF current here, and the leftover current is V out SCF as shown here. Okay. So now, if I remember, I wanted to take out any current from SCF going into the output. So I'm going to now throw away this term here, and I end up with this transfer function. With this block diagram, and if I write the transfer function for this, I end up with an equation that shows like this, which is the 0 is at 1 over RFCF, and there is no pole. Right. So, and this is again going back to removing this capacitor. So all we need to do now is that we need to add the CF capacitor that we are planning to add at output to ground. And Vx node to ground as shown here, and I also would want to have a voltage controlled current source whose value is controlled by Vout, Vout times SCF really. Okay, so if you can do that, then the overall LDO is going to look something like this. The CF can be combined with the output capacitor, and this is really the current that is injected into the Vx node. Okay, so this will give you the 0 frequency, and by choosing CF capacitor, you can always place the 0 to be within the unity gain frequency. Again, one way to implement this voltage controlled current source is shown here. This feedback loop here forces V out, this is V out, across the capacitor SCF, and this current mirror ensures that that much amount of current is drawn out from the Vx node. Okay, so this is actually implementing essentially V out SCF current taken out from node Vx. Okay, the benefits of doing this, all this hard work, is really that you can choose your C naught to be any capacitor with without any specific consideration to the ESR. Okay, so the third compensation scheme that I would like to discuss is the following. We would like to now, instead of adding zeros, we would like to now push out the pole frequency to outside the unity gain frequency so that the phase margin requirements are met. So for that, we can, if you look at the poles and pole frequencies, the omega PL is 1 over RL C naught. The high frequency pole, again, I'm still thinking the output pole is dominant. The high frequency pole is at the error amplifier output, where C1 includes all the output capacitance of the error amplifier, CGS, and so on and so forth. So really, I would like to reduce either C1 or the output impedance of the amplifier. Changing the output impedance of the amplifier is not an option really, because it will reduce the gain of the other amplifier. So all I'm left with is reducing C1, but in practice reducing C1 is also difficult, because if you have to ensure that the dropout voltage is few hundred millivolts with a load current of 50 milliamps, the size of the device is set. And once the device size is set, the CGS, or for practical purposes, the C1 is set as well. So for a given load and VDSAT requirements, the C1 is fixed. So in this context, what would be useful to do is to sort of decouple the pole, the output frequency, from the output impedance. Again, as trivial as it might sound, using a buffer to shield C1 capacitance from the amplifier output is very commonly used. So in this context, the low frequency pole remains the same at the output, which is 1 over RLC naught, and the high frequency pole now becomes the output impedance of the error amplifier times whatever is the leftover capacitance at this node, which I'm denoting as Cx here. So as you can imagine, the input capacitance of the buffer must be much smaller than whatever the gate capacitance of this device is, and the newly added pole is really the output impedance of the buffer times the capacitance here as shown. So the requirements on the buffer are very low input capacitance and also very low output impedance. That's what typically output buffers are supposed to do anyway. So one way to implement the buffer is, well, we can perhaps use a source follower. In many practical applications, this could possibly work as long as Vin is large enough. But in order to reduce the output impedance, basically the output impedance of a source follower is roughly 1 over GM of this transistor. As a result, you will end up burning a lot of bias current. And this is conflicting with the quiescent current that we were trying to minimize in the first place. So one way to actually reduce the output impedance here is to use some simple poor man's feedback. Again, most of the details are in these references. So you can use feedback to lower output impedance. One way to use that is the so-called shunt feedback. Your error amplifier output is here, and you would want to place a buffer between error amplifier output and the gate of the pass device. So by adding the shunt device MS, we are going to greatly reduce the output impedance. The way to think about this is, when you change output impedance is when you wiggle VG, how much current do you draw from the output. So here, when you wiggle VG, you will see a large gain from this point to Vx, because these two transistors act like a common gate stage. So the gain from here to here is the transconductance of this stage times the impedance at Rx, so that is GMB Rx. So when you wiggle this by 1 millivolt, this wiggles by GMB Rx times 1 millivolt. So the net current drawn here is really GMB Rx times GMS. So the output impedance is roughly equal to 1 over this term here. So the larger the gain you have here, or the larger the transconductance you have here, will greatly reduce the output impedance. Okay. This typically burns much lower power compared to the case where you don't have the feedback and you keep just increasing the bias current. So far, I think I have talked about LDOs with large output capacitor. Now I'm going to sort of switch gears and talk about cap-less LDOs, meaning the output is taken at this point, and the stability has to be ensured in the presence of any capacitance that one might add at the output, and we can also have a little bit more degree of freedom with the capacitance we choose here in order to stabilize the feedback. Right. So since C0 is internal to the LDO, typically its value is few hundred picofarad for area reasons. So once you change the output capacitance from few microfarad to few hundreds of picofarad, we'll have to think stability slightly differently, because now the pole at the output of the error amplifier is, if not way smaller, comparable to the pole at this node. Again, the pole at the output really depends on the load current, but for typical load currents, 10 milliamps to 25 milliamps range, it turns out that the output pole at the error amplifier becomes the dominant pole. Okay, so now we have opportunities to do Miller compensation because the output is not really setting the dominant pole. Under this condition, I'm going to consider two cases, Miller compensation and Cascode compensation. And since Miller compensation is very well known, I'll mostly focus on the second way of compensating. So Miller compensation is simply adding a capacitor from here to the output. But generally, Miller compensation is not very good for multiple reasons. Number one, the stability depends on what kind of load capacitance you have. Right, so if you keep increasing the load capacitance, the second pole moves in, as a result compromising the stability. Right, so in practice, you would want to choose this compensation capacitor to be some fraction, maybe 1/2 or 1/3 of the load capacitance, in order to retain stability across all possible capacitance values. So for this reason, Miller compensation becomes very sensitive to load capacitance and also load current variations. That's number one. Number two is at high frequencies, this capacitor is going to short the current source here. As a result, this will become a low impedance path from VDD to ground, and all of the noise at the input will appear at the output. Or in other words, the high frequency PSR is poor for Miller compensated LDO. So what I would like to do now is focus on a slightly different way of compensating these things, and hopefully will give the benefit of smaller compensation capacitor in the presence of large load capacitance. So the way this is structured is the following. You have your first stage, and you have denoted by M1 R1. You have the second stage denoted here M2 R2. The load capacitance of the first stage is C1. The load capacitance, everything combined, is C2. And what we are going to do is, instead of connecting a compensation capacitor from gate of M2 to the drain of M2, I'm going to use a common gate or current buffer between one plate of the capacitor and the other plate of the capacitor. So the way to think about it is, consider the case when GM3 is very large. So the impedance looking into GM3 is very small. Then what happens is you have feedback. It's essentially equivalent to connecting this node to there, but there is no feed forward. Meaning the output impedance looking into the drain of M3 is very large, and therefore there is no feed forward. So the first thing to expect from this compensation scheme is that there is no zero. In the presence of some finite GM, you will find that the zeros are at relatively high frequency. The other thing to note here is the power supply rejection at high frequencies is going to be a lot better because there is no diode tight connection that we have seen in the case of Miller compensated LDO. And I'll show you in the next few slides. It actually pushes this feedback, pushes the output pole to much higher frequencies, and as a result, even if the load capacitance varies by 10x, let us say, the stability of the LDO is not compromised. So that's probably the more useful result in all of this. So let me briefly describe this compensation capacitor sort of hand waving way, and then I will provide you with exact equations, which will take a lot of time to actually verify. So I'm not good at that. So just trust me, the equations are right. Otherwise, you can look up in a textbook. But this is something I would like to talk about because this is a little bit more useful in design. So first thing we want to ensure is that the added capacitor actually is making a dominant pole at the output of the first stage. For that reason, I would like to figure out what the output impedance is at this node. And if I want to figure out output impedance, I'm going to apply a test voltage source here, VT, and measure how much current is drawn from that test voltage source, denoted here as IT. So the current drawn from here is essentially whatever is the current flowing in this path, which is VT minus whatever is this value, voltage, which is Vt times Gm2 R2 negative, right? That is this term. And if Gm3 is very, very large, then I can just ignore the impedance between this point and that point. And if Gm3 is not very large, then you can include, and this becomes slightly messy, but if one over Gm3 is very large, then I'll assume that this thing is shorted there. So I got this IT. Therefore, impedance looking into this node is 1 plus Gm2 R2 times Cc, or in other words, Cc is amplified by the gain of the second stage. That's the typical Miller multiplication. That in itself is not super interesting. And the more interesting part is at higher frequencies, where the capacitance moreover behaves like a short, I would like to figure out what the output impedance is going to be. Previously, when this Gm3 is not present, this was a diode transistor, and the impedance was simply 1 over Gm2. But in the presence of this M3, again, I'll have a small voltage. I'll wiggle this voltage by Vt, and I would figure out what the current is drawn by this branch. So if you wiggle this voltage by Vt, then this M3 and R1 forms a common gate stage. So this voltage here is Gm3 times RT. So the gate voltage of M2 is Gm3 times R1 times Vt. Therefore, this current here in M2 is Gm2 times this, and there is some small current through R2 as well, but this is the key takeaway. So what this means is the second pole now is not at Gm2 over C2, which it was previously, but it is pushed out to much, much higher frequencies. In this particular case, Gm3 times R1. So if Gm3 times R1 is 20, then your second pole is 20 times farther away. Why is that important? That is important because now for the same amount of phase margin, we can live with 20 times more compensation capacitor without compromising stability. Okay, so for that reason, cascode compensation is extremely useful for driving large capacitive loads and large variable capacitive loads. So this is how the LDO would look like once it is cascode compensated, and these are the exact expressions. In practice, I don't have a figure. If this amplifier is implemented using some cascode topology, either a folded cascode or a telescopic cascode, then this node is already available. The cascode node is already available inside the amplifier, and therefore an explicit common gate amplifier such as this is typically not required. Okay, so the exact expressions are here. Let me just very quickly go through how the pole frequencies are going to vary when you change the load capacitance. For very small capacitances, if you put C0 to be very small compared to other capacitances, the poles are going to be these. And when you keep increasing the output capacitance, the non-dominant pole sitting at the output moves in, and if you keep increasing it farther and higher and higher, then at some point the output pole actually becomes dominant, and in that case the pole frequency is given by this, and the non-dominant pole happens to be at the output of the other amplifier, which is given by this. So what we would like to really know in practice is what are the values for our compensation capacitor when C0 is changing by a lot, right? So for that reason, I would like to figure out the stability quality factor, which I'm defining as the ratio between second pole frequency to unity gain frequency. If it is 10, it's great. If it is 0.1, well, it's not good because the phase margin is going to be compromised. So you can figure out what values of load capacitance is this going to be stable by simply differentiating the expressions, the messy looking expressions I showed you for P2 and omega GF in the previous slide, and figuring out the C0 for which the loop remains stable. So the end result is shown here. The load capacitance is plotted on x-axis, and the phase margin is plotted on y-axis for some choice of CC. I don't remember now, but the key takeaway is that even with orders of magnitude variation in load capacitance, one can ensure that the phase margin is good. I mean, obviously, I'm slightly cheating here because I designed it to be 90 degrees phase margin to start with, but regardless, this tells you what could happen. Right? So the similar thing can be applied for variations in load current, and you can see that since we are not very sensitive to GM2, variations in load current will change GM2 a little bit, but in the end they won't affect stability because the second pole again is much farther away from the unity gain frequency. Okay, so that is all about compensation of LDOs. So in the next maybe 20 minutes or so, I'm going to talk about power supply rejection properties of low dropout regulators. So so you have three important blocks that one needs to worry about. One is the reference generator, an amplifier, and the pass gate. So we would want to evaluate how much of this noise on input leaks through each of these individual blocks. It turns out that they're all important, but some are easier to combat than others. So in the next few slides, I'm going to again revert to my small signal or signal flow graph that I have shown here, and I'm going to now add PSR of the error amplifier. By PSR, if you may recall from my earlier slides, is for example for the error amplifier, PSR is defined as how much of the supply noise is going to appear at the output of the error amplifier. So that ratio is the PSR of error amplifier, and similarly you can also define the PSR of your reference generator, and those are denoted in these places. So how much of input will appear at the output of the error amplifier is dictated by the PSR of the error amplifier, and similarly the reference generator. So I can now write the trans functions from V in to V out in the presence of noise, in the presence of finite PSR of the reference generator and the error amplifier by the following. Again, this is exactly the same analysis that I have shown here, but these things look a little bit more complicated because I need to go through the same analysis that I have shown. I mean, I don't want to spend too much time on this, but the key takeaway from here is that V out or V in for the reference generator is low pass. So we are going to discuss in the reverse order. So first I'm going to talk about how to mitigate any noise leakage from the reference generator to the output, and then we'll come back and talk about the pass device and the error amplifier shortly thereafter. So the reference generator is actually quite easy because there is no current actually flowing into the error amplifier. As a result, if there is any noise at this point, you can simply place a very low pass filter here to suppress any noise appearing at the input of the error amplifier. Now, obviously, this low pass filter has to be much lower in bandwidth than the bandwidth from here to the output, otherwise it wouldn't really do anything. So if you have enough area, then you would really place a large capacitor in order to suppress the noise from the reference generator. So I'm not going to spend time on this, but rather I'm going to focus on the PSR of the error amplifier and the pass device in the next couple of slides. So let's start with PSR of the error amplifier. Again, the same analysis can be applied to a little bit more involved circuit such as telescopic or folded cascode, but since of the space requirements here, I'm going to do this exercise for a simple phi tac. Here, what I'm interested in is figuring out VDD over V out. And again, the reason for doing all this is I would like to pick an appropriate error amplifier topology and an appropriate pass device so that my PSR is maximized or minimized, whichever way you define. Okay, so for that reason, I'm after figuring out what is a good error amplifier topology for use in an LDO, for example, with PMOS pass element or NMOS pass element. So V out over VDD is short circuit transconductance GM times output impedance R out. R out is, you guys have done it many times, it's just the parallel of these two. And if you want to figure out short circuit transconductance, that is not very difficult. You'd short the output because the definition, the Norton equivalent transconductance is output is shorted. You wiggle the input VDD and measure how much output current is here. So really, I out is whatever is the current here plus the mirroring current, that is 2Ix, and there is some current through RDS4, that is VDD over RDS4. So if you want to figure out this IX current, the way I'm going to do it is I'm going to figure out what this RX is to ground, and IX is simply VDD over 1 over GM1 plus RX. In order to figure out RX, this is a cascode impedance where M1 is the cascode transistor and M2 is the main transistor, and the impedance looking into the gate of M2 is 1 over GM2, and this is the impedance of the current source. So if 1 over GM2 is much smaller than this R, what I really have is RX is simply GM1 RDS1 times the impedance looking into this, which is 1 over GM2 plus RDS2. Therefore, RX is 2 RDS1, and if RX is known, IX is VDD over the impedance from here to ground, which is 1 over GM3 plus whatever we calculated here, 2 RDS1. And if this is much larger than 1 over GM3, this is VDD over 2 RDS1, and 1 over GM is RDS1 parallel RDS4. So what this means is really all of the noise you have on the supply voltage appears at the output, because the power supply rejection of this kind of an error amplifier is 1. This might sound like a terrible thing to have, but as we will see, we are not interested only in the error amplifier of individual blocks. I'm really interested in the PSR of the entire LDO. So when we put this in the context of entire LDO, this actually may be a very good thing. Similarly, you can do the same thing for the second kind of error amplifier where you have PMOS devices. And just for simplicity's sake, if you assume that the output impedance of this current source is very large, then even if you wiggle the supply voltage, the current to the current source doesn't change, therefore Vout doesn't change. So the PSR is infinite. So Vout is 0 independent of V, right? So that is to the error amplifier. Now I'm going to quickly do the same calculation for the output stages. So if you take the output stage of a pass transistor, this is my pass transistor here, and if I wiggle the supply voltage, I'm figuring out how much of this is going to appear at the output. This is a common gate stage, so Vout over VDD is given by this expression. So there are actually two scenarios. The first scenario is I'm assuming that none of the supply voltage is going to appear at its gate, or in other words, M1 gate of M1 is not coupled to VDD. It's perfectly decoupled. It has nothing to do with VDD, right? In that case, the Vout over Vin happens to be this value. And the second case, when you have some means of providing all of this VDD at the gate, right? So you already have a hint how to provide that. But regardless, if all of that VDD is provided at the gate, then you just eliminated the VGS component of the current, and as a result, Vout over VDD is just a resistor divider between RL and RDS of the MOSFET. Okay, so in that case, PSR is just a resistor divider. You can do the same exercise for an NMOS output stage. The results are slightly different. In this case, if the output is totally decoupled from the noise, VDD, then this becomes like a cascode. Therefore, any noise here gets heavily attenuated by the cascoding action of M1. And in fact, you can easily show, as I have done here, Vout over VDD is 1 over GM1 RDS1, which is the gain of the cascoding device, which is essentially the pass device in our case. In the second example, where gate voltage is tightly coupled to VDD, what you have is a source follower, therefore Vout over VDD is equal to 1. Okay, so now if you want to choose your error amplifier and output pass stage, obviously based on the discussion we had so far, there are essentially 4 possibilities that I have listed here. But for best PSR, there are 2 good cases. In case 1, when you are using a pass transistor output stage, you want to have any noise on VDD appear on its gate so that the VGS is coupled, or VGS is 0 ideally. Right? So for that reason, I would like to use type A error amplifier that I have shown here. And conversely, if you are using an NMOS, so NMOS output stage, then you would use type B error amplifier. Again, the overall PSR actually depends on what kind of output stage you have. NMOS is way better, but unfortunately, you will also have to deal with a very large dropout voltage that comes with an NMOS output stage. Okay. whatever I have done so far is somewhat hand waving, high level picture of what kind of an amplifier and what kind of output stage must be chosen. Now I'm going to dig a little bit deeper into what kind of power supply rejection performance one can expect out of an LDO that looks like this. Again, in terms of first principles, this is no different from doing a frequency response of a standard amplifier, except for the input is at VDD, output is at out. So you can draw the small signal equivalent model such as the one I'm showing here, and long behold, one can calculate the trans function V out for VDD, which is the power supply rejection, to be this. Here, let me just define a couple of terms that I would like to use in the next slide. SVDD is defined as RL over RL plus RDSP. This is the case when the gate of the pass transistor is not moving at all. This could happen when there is no feedback and when VDD is tightly coupled to its gate. Then you just have a resistor divider between RDS of that pass transistor and RL, which is denoted as SVDD. And if you trust me that these calculations are done properly, this is the PSR trans function. So instead of doing this, what I would like to do is instead I would like to show you the PSR plot without actually using the trans function analysis. So let us start what happens at very low frequencies, meaning the supply voltage is changing very slowly. So which means that if the supply voltage is changing very slowly and the reference voltage is totally decoupled from VDD, which means that reference voltage is not changing with VDD, the feedback loop now is essentially going to force V out to be at VDD, and any changes in VDD are going to be rejected at the output. How well are they rejected really depends on this loop, or in other words, the loop gain. So at very low frequencies, whatever you have when there is no feedback action, which I just defined as SVDD, gets attenuated by 1 plus loop gain. Okay. So if this moves at 1 Hertz and if the loop bandwidth is at 1 megahertz, then V out will see only a very small fraction of VDD, and what that fraction really depends on what the loop gain is. Now, if you keep increasing the supply noise frequency, you are going to move in this direction. This is frequency. This actually should be log omega. Then what happens is when you hit the dominant pole, which is sitting at the amplifier output, the loop gain is going to drop off at 20 dB per decade. Okay, so which means that the loop's ability to suppress noise from supply is also going to drop off at the same rate, and that manifests itself as a degraded power supply rejection beyond the amplifier output pole frequency. Okay, so now if you keep increasing the noise frequency further, you are going to hit the loop gain unity gain frequency, at which point the loop gain is actually 1. And above that frequency, the loop gain is less than 1, there is no feedback action. So 1 plus loop gain essentially is 1. Right? So for frequencies beyond the regulator unity gain frequencies, there is no feedback action, so what you end up getting is SVDD. So for frequencies beyond the regulator bandwidth, this is SVDD. Just to make it look nicer, I didn't plot the Bode plot, this is the real plot, so it doesn't stay flat. So once you hit the pole at the output, which is governed by the output capacitance, what you will end up finding is this capacitor is going to short the output load resistance, or in other words, it's going to take all the noise instead of it flowing into the load resistance, so the power supply rejection sort of improves at very high frequencies. Very high frequencies being beyond the second pole. Okay, so that is the typical power supply plot, and that is actually reflected by this trans function, which one can calculate from first principles. So clearly, in many applications, this is somewhat undesirable because this peaking happens to be around the regulator bandwidth, which is 1-2 megahertz, and the switching frequency of the DC to DC converters are also in that range. So I'm contradicting myself by saying that the switching frequency is at 1 megahertz. The power supply rejection is at its absolute worst at 1 megahertz. So we are not I just wasted 1.5 hours of your time. But jokes aside, so there are ways to actually improve the power supply rejection by doing one of these things. The first and foremost is, actually this is quite useful, is the power supply rejection of your NMOS output stage is way better than a PMOS because of the cascading action we described earlier. So I've seen many people, and we have ourselves used it a lot, is this poor man's LDO, where we don't even use a regulator. We just generate the reference voltage to the NMOS by filtering the heck out of VDD by using RF, CF. And if you have access to one of those native devices which have threshold voltages in the range of 100 millivolts, 0 would be perfect. You would use one of those devices here to mitigate some of the dropout penalty that we discussed previously that comes with an NMOS device. And if you plot, you can easily calculate the PSR. There is one PSR that comes from the pass device, and there is another PSR that leaks through RFCF and the source follower. At very low frequencies, it is dominated by the leakage through RFCF, as shown here, and at high frequencies, this is the cascading action as we discussed previously. So what we really want is we have to ask ourselves how much of low frequency rejection do you really need? So if you are using this LDO, for example, for supplying an oscillator, right? So if it is a standalone oscillator, you're sort of doomed. But if this oscillator is going to be embedded in, for example, a PLL feedback, the PLL itself is going to provide some low frequency rejection. So in which case, you don't really need to do even more stuff of regulating or suppressing low frequency. The other loops that you are going to use this LDO with may suppress some of this, and all you care is this. In those applications, this can be quite useful. Okay. Again, if you don't have one of those magic native devices, you can also use a charge pump based voltage booster. But again, these are the things that I try to avoid. So the other sort of way to make the LDO power supply rejection of the LDO slightly better is previously we had made the output pole to be dominant, but consider the case when if you can make the LDO output pole dominant. This requires a large capacitor as we have discussed previously, but if one can do that, then the first pole is going to be the output pole, right? So at the output pole you have a that is because of the large output capacitor, so it is going to reduce the output impedance. As a result, your power supply rejection doesn't actually get worse beyond the first pole frequency, as long as the first pole frequency happens to be the output pole. The penalty, the problem of doing this in an integrated LDO is that you will need nanofarads of capacitance to achieve compensation in this manner. Okay. Again, if one doesn't work, probably two is better. So in that case, not for quarterbacks, I guess, but here it is. You have two LDOs cascaded, and again, when you cascade LDOs, one needs to be a little bit shrewd in terms of choosing the power supply rejection curves properly. For example, if one LDO looks, the first LDO looks like this, the second LDO can look like this because you have good rejection at this frequency. So no need to optimize both the LDOs to give world's best power supply rejection, but the cascading effect has to be considered in the design. But generally this is not very practical, at least for low supply voltages, because the dropout voltages add, even though the power supply rejection ratios add in the dB scale. The last thing that I would like to discuss is somewhat of a cheating type LDO, which I'm denoting here as replica based LDO. Here, what I would like to do is not have my output stage inside the feedback loop. The reason for the basic thinking behind this is the following. Remember when we wanted to make the output, when we made the output pole dominant, we ended up with very poor supply rejection because of that zero or the peaking in the power supply rejection curve, right? So I would like to, if possible, not have that peaking. One way, as I have indicated a couple of slides ago, is to make the output pole dominant, but I also pointed out that that requires massive amounts of capacitance because of the feedback. So the thinking here is if I can remove the output stage and place it outside the feedback loop, and then if I, this is a big if I have a replica resistor which can mimic the IV characteristics of my load, then I'm going to use that replica here. Let's say you have a perfect replica, just for argument's sake. Then if the load, then by regulating this node voltage to V in, you are indirectly regulating V out also to VREP, right? This is true as long as these two replica and the main regulator, main load match. There are many places where you already know the load, so you can sort of mimic this behavior. You can find one example in this reference 8 where this has been used to achieve almost 40 dB improvement in power supply rejection. This is not for a generic LDO which can be used in any place, but if you know the load and if you can come up with a replica of load, this can be extremely useful, and I'm going to show you why this is going to be useful. So first things to note are the output is indirectly regulated to the reference voltage to the extent that the replica and the node match, and I have pointed out that the PSR is better. So again, the brute force way is you draw the small signal model and you end up with a trans function that looks like this. This trans function is essentially the same as what we had before. Where instead of SVDD that I have indicated earlier, this is now a voltage divider between, if there is no feedback and if this is tightly coupled to VDD, it's a voltage divider between RDS of this transistor and RL, that is SM, and the rest of it is the same, except for now, luckily we have a pole at omega D, where omega D is the pole formed at the output between RL and CD. Okay, so now the nice thing about this is I have independent or one other degree of freedom to set this omega D wherever I choose to. Earlier, I had to worry about stability when the same pole is sitting at the output of the regulator. Now, by placing it outside the regulator, I have this other degree of freedom to choose CD and RL based on how much power supply rejection do I need and how much area do I have in terms of realizing CD, right? So, so now what happens is if I have the ability to choose the newly added pole at this node, which is RD, whatever is the impedance at this node times CD, then and if I have the ability to choose at very low frequencies, lower than the amplifier, the LDO dominant pole, then what I end up seeing is for frequencies beyond omega D, the output pole or the output capacitance CD is going to shunt all the noise current, so your rejection actually improves. And once you hit omega A, the supply rejection properties of the LDO itself are getting worse, and as a result, that gets compensated by this 20 dB per decade roll off. And as before, when you hit the output pole of the LDO, you start improving. So as you can see, you end up with very large improvements in power supply rejection ratio if one can do this. The only caveat here is that one needs to figure out a good replica. And reference 8 shows one example for an oscillator, and if you have a static current like TIAs or any front-end stages that consume static current, then it's not easy but possible to actually come up with a replica that matches the IV characteristics of your load. Okay, I think this is all I have. We are up in our time. So in summary, I think we went through the important performance metrics of LDOs, and then we spent some time on stabilizing these LDOs when the capacitor is off chip or on chip. And the challenge really here is to design these LDOs to be stable across varying load capacitances and load currents. And in those terms, using a cascode compensation seems to be one way to do it, and there is a raft of literature on this topic addressing some of these concerns, and hopefully some of these ideas would be useful, if not directly in design, hopefully to read those papers and understand them slightly better. And towards the very end, we also talked about power supply rejection ratio, and when you want to optimize power supply rejection, it's a matter of figuring out what kind of error amplifier and pass device combination yields you the best PSR. I think that is all I have. These are the references, and I would like to thank these guys who did most of the work. Eric had the envious job of coordinating with an academic, and he knows what that means now. And as promised, let me just go to the first slide. I don't know how to go to the first slide. Okay. So I guess you can close your eyes if it is going to make you dizzy, but normally one and this works, it's not working.
So I'll open this session up for questions. There's a couple of microphones here in the middle if you would like to come forward and ask Pavan some questions about LDOs. Well, while people are making their way over, I'll go ahead and start with a question. So maybe this is maybe more a little bit about using LDOs, but sometimes people will use a ferrite bead, like in conjunction with maybe their buck converter or their LDO, to just get a little bit of extra loss, right, and supply rejection. Do you have any thoughts on that? Of like, you know, people put them different places and use them different ways. If it matters, if it helps, do you know what I'm talking about?
Let me understand the question properly. So, what is an appropriate place to put the LDO?
Well, no, a ferrite bead. You know, sometimes people use ferrite beads in addition to their regulator solution to get a little bit of extra rejection.
Okay. Yeah, if you have good ferrite beads, it's always a good idea to use. But if I mean, most of these LDOs are finding their use in on-chip applications, in which case ferrite bead is typically not. If I want to be polite, typically not an option.
Sure,
or is never an option.
Right.
But for external LDOs, anything that shields noise in the first place before it appears at the LDO is generally a good idea.
Great. We have a couple questions.
Thank you for your introduction about LDO design. I have one question about your compensation design. For the Cascode compensation method, I see you need additional current source to generate a compensation circuit. But will this reduce your current efficiency of the regulator?
No. So I think the question is, sorry, the numbers are not working on this one. So for cascode compensation, for the current buffer, I think I have shown it as requiring a bias current. The question is, the question is related to that. But really, in fact, is sorry, not this one. You don't really need this explicit branch. Imagine that this M3 transistor is used as a cascode at this point, this is slightly difficult to. Imagine M1 is cascoded, and you have access to the source of the cascode device. The capacitor in that virtual, not visible cascode can be used to connect that point. So this branch is sort of reused in this branch. Is the question? Is that the question? So, what I'm saying is, if the question is, we need these additional current sources, my answer is you don't need this. You can think of this M3 being part of the cascode stage of the first stage, and you can
merge string 1 and 3, and
Yes.
M3 becomes the cascode for M1, and
And then
current
the-
source becomes R1.
current source is R1.
Okay, thank you.
Yeah, I'll hang around. You can come and talk to me. If I can draw stuff, it'll be easier.
Couple of questions. Okay, first easy one. A lot of the times the load is primarily CMOS logic, and CMOS logic has an anti-characteristic of drawing no current when you stop the clock, which you often have happen. And the wasteful solution is to just burn some wasted current just to keep the current from dropping to zero because everything fails. Any suggestions on what to do when the current drops to zero?
I think if you pigeonhole me by saying I want good rejection and no load operation, then that's a difficult problem. But if you give some room for somewhat degraded power supply rejection, some of these resistive based digital LDOs, where they are just physically changing the resistance, they have no rejection. But those resistors can be changed rapidly in order to change the output instantaneously when the load current changes from, let's say, 0 to tens of milliamps, would be one way. But if you want to have good rejection, then making the loop faster and faster probably could be one way. Or yeah, I'll stop there. We can talk later.
Okay. Towards the end, you gave a couple examples of that, swapping who's dominant pole. And you want to comment on the transient performance, capabilities.
Yeah, so if you have output pole dominant, there are two ways to address load transients, right? One is if the load varies, have infinitely big capacitor to not let the output voltage change. That's one extreme. The other extreme is have infinite bandwidth feedback and regulate the output voltage to not change. Right? So these would be the two extremes. If you make the output pole dominant and have a very large capacitor, then what we are really trying to do is not let the output voltage change by having a big enough capacitor. And in this context, if you have any ESR and all that, it's going to degrade. You're going to get overshoot and ringing, and the transient response is degraded. But that is one way. The other way is you try to make the loop bandwidth as fast as possible, and as a result, you can regulate the output to not go beyond the error tolerances, even in the presence of load current variations. So, which one works better? Well, in many cases, you only can make the loop bandwidth faster, but if you already know that your digital logic is going to switch now, and if you can give me like few tens of nanoseconds advance notice, then you can also prepare the LDO to be ready by assisting the LDO to supply instantaneous currents at startup or power on.
One more. There's a class of LDOs that are starting to show up in designs where they essentially combine a series and a shunt all the way to the output. Any comments on that?
I am not familiar. I think what the question is, if you have an LDO like this, what I have talked about is mostly series regulation. The other way, I think Eric is trying to help me here, is if you have some other regulator here which reduces the output impedance by a lot, then that actually improves the load regulation as well. So combining the series element with the shunt element, I have sort of hinted this in the context of lower and output impedance of a buffer, that greatly improves the load transient, because in the end, load transient performance is related to output impedance. Anything that you can do to lower output impedance is naturally going to help the load transient. So if you can figure out a way to combine the series element with the shunt element, that's bound to help load regulation. But I myself haven't designed any of that. So if you have any more questions, you can talk to Eric after this. Yeah.
I have a question about also LDO regulation. So my understanding is that there are now some applications that require a lot of voltage domain, and some of that voltage domain actually have very small power consumption. They just require an LDO to provide a steady supply. So the current consumption of that voltage domain is small, but it would still require good power rejection ratio. So I'm wondering, so when we go about designing LDO for that purpose, how do we, to what extent can we reduce the quasi current, and what are the limitations?
So I think if I understand your question correctly, if you're asking me for applications where output current is very small to start with, how do we design an LDO?
Yeah.
That is problem. If that is the question, yeah, thank you. That's a somewhat easier question compared to the load current can vary over a range, and you want to ensure that the quiescent current and power supply rejection properties to be good even when the load current is small. So I'm not going to answer the difficult question because you didn't ask me that. The simpler question boils down to how one can design the error amplifier efficiently. So there are many ways to actually design this error amplifier with nanoamps of bias current. And since the bandwidths are not important in the applications you are referring to, the quiescent current can be tens of nanoamps if you are only supplying few tens of microamps of load current. So the current efficiencies still can be maintained, but it will boil down to actually designing the error amplifier with very small bias currents. And actually just operating them in sub-threshold is what I have seen, and bias currents can easily be in the tens of nanoamps.
I see, so just a narrow band, low power error.
Correct.
Okay, thanks.
Now you can appreciate why the other question can be hard.
Question about the flexibility contribution of the pass device in the different contribution that you showed. So on the LDOs help that, let's say, if the LDO is used to suppress the noise from being as used by the PLL, then it does reduce the DBA, but then it has a flexibility contribution. So how does it respond?
For PLLs, I'm not entirely sure if the noise from this stage is going to impact, but regardless, the flicker noise from this stage can be made small simply by increasing the size, right? And number one. Number two, if you are again thinking in terms of a PLL, which is, I'm presuming that this LDO is supplying the oscillator, in which case the low frequency noise is rejected by the PLL loop itself. Unless you have a PLL loop whose corner frequency is in the vicinity of the flicker noise corner of this, we'll have to do something special. But in most practical cases, the flicker noise corner happens to be less than the PLL bandwidth, which is few megahertz for LC and few maybe 10 megahertz per ring, in which case the PLL loop itself is going to suppress the flicker noise. In that case, no need to do anything special. But in cases where you are interested in absolute noise requirement, then one will have to increase the size of the output stage. Right? So that comes with all the other trade-offs that we discussed.
If there's no more questions, I'll make a couple announcements and then we'll wrap up. I wanted to remind everybody that the sessions this afternoon will start at 1:30, except for session 8 starts at 1 o'clock. There will be exhibits this evening from 4 p.m. to 8 p.m. And if you're interested in the luncheon tomorrow, please purchase a ticket. I believe they said this morning that there were a few left. Please do that essentially before you go to lunch. And those are $40 at the registration center. Let's see, there will be a poster session this afternoon. And one final reminder, remember to go to the website and rate the speaker today. And that'll help us provide feedback for future educational sessions. So with that, let's thank the speaker once again. Thank you.